Okay, hi guys. So in this lecture, we'll be discussing about on some more examples on alkyl halides being substituted by nucleophiles or examples of SN2 reactions, and then later in the lecture, we'll be seeing some of the name reactions like Finklestein, Williomson, ether synthesis, and the likes. Okay, so let us see the first example. We have IETCH3 and H here, so it is being attacked by KSH. So what would be the configuration after the attack? Obviously after the attack we would have something like SH here, CH3, H and ET here. Okay, so whatever be the configuration of this is here, exactly opposite would be formed. Okay, and second example is, let us have this. So what does happen if T here, Cl here, H here and ET here, this substituent here. So if it's getting attacked with PSH minus, PS minus, so we will have the answer something like this: SPH here, D here, and this atom's configuration will remain the same. Okay, we have third example as this, where we have Br, HD and CH3. This on reaction with KSH would form something like this KSH will replace this, and the configuration of this would change. So D will come here, H will come here, HD and CH3. Okay, so now what happens is, supposedly, so if the for this, let me write it down. So if the leaving group is on equitable, then in the SN2 reaction nucleophile will be at axial position, right? So if leaving group is on equatorial position, then in SN2 reaction nucleophile will be at axial, and vice versa. Axial and equatorial, this would be vice versa. Okay, so let's talk about this case wherein we have Br here, D here and H here, this group here. So it on reaction with KCN minus, obviously in the product we would have something like Cn on the lower side, D in the axial position, D occupies the axial position, and this carbon's configuration will not change. Okay, so we'll now see something about Finkelstein reaction. So in Finkelstein reaction, this is also called halide exchange reaction. Halide exchange reaction, in which, let's suppose we have an AI on reacting with RBr, gets in the presence of acetone, we actually have formation of Ri plus NABr. So here you can see that we have a I minus and here Br minus, and the stability of I minus is also higher in the solvent called acetone. So why does this reaction go forward? Any guesses? This is the stability order. So shouldn't it go into the backward direction, because I minus is more stable than Br minus? So you are right if you have thought that this should go in the backward direction, as I minus is more stable than Bi minus. But the driving force for this reaction, and the reason why this doesn't go in the backward direction, is the PPT formation of NABr. So as soon as this reaction tends to go forward, NABr PPT would be forming, and the formation of or the precipitation of the product called NABr is the driving force for this reaction. Okay, so let me write it down formally, that the precipitation of NABR is the driving force. Okay, so let us talk about Williamson ether synthesis. Okay, so in Williamson ether synthesis, we have these products. So RO minus, the general name is alkoxide. So similarly we can name CS3O minus as methoxide, C2H5O minus as ethoxide, then this as tertiary butoxide, and this as phenoxide. Then actually in the reactions what happens is, if we have RO minus and it is reacting with R dash Br, what will happen is the formation of ether would take place via SN2 mechanism. Okay, if we, so on a concrete example, if we have replacing CS3 and ET in place of R and R dash, we have something called ethyl methyl ether. And if we have something like ETO minus reacting with CS3Br, then also the same product. Okay, so when phenoxide or when alkoxide react with alkyl halide to form ether, this is known as Williamson's ether synthesis. So let me write it more formally, that when alkoxide react with alkyl halide to form ether, this is known as Williamson's ether synthesis. Okay, so we have to, next question is, we have to prepare the following compounds with the help of your Williamson ether synthesis mechanism. So the question is, prepare the following with Williamson's ether synthesis. Okay, now we have something like this. So we have CS3O. So how can this be prepared with Williamson ether synthesis? The answer is simple. We can use these two as reagents or these two as substrates. We can have this with CS3Br. Okay, how do you prepare this with Williamson's ether synthesis? pH OCS3, you can actually have PHO minus plus CS3Br to get to this reaction, and you actually cannot have this. You can have, but you cannot have something like this, because in the intermediate this will get a partial positive charge. So due to the formation or of highly unstable aryl halide or aryl cation, this will not take place. Okay, how do you prepare this? So you can prepare this from this plus CH2 CH3Br. Okay, but the positive charge on this would actually not be preferred here. By positive charge I mean the Br here and CH2 CH3 or CH3 CH2 O minus should not be the case, because we have a positive charge on we'll have a positive charge or the formation of a partial positive charge on in the carbo in the intermediate state, in the intermediate state. Okay, how will you prepare this? So how will you prepare this? So for this we can have two options, that we can either have pH O minus and something like this, or we can have pH Br plus something like this. So in both the cases they are not feasible, because in the first case it would be a vinyl cation formation, and in the second case it will be a aryl cation formation, both of which are highly unstable. Okay, so in both the case in this case no possibility is there of any substrates or reactants. Okay, let us look at the fifth example, wherein we have something like this. So how can you form this? You can actually have CH3 minus with Br here. Okay, or you can actually have O minus with CH3Br here. Either way you can actually attack it. Okay, so let us define what is a simple term called nucleophilicity or nucleophility. Nucleophility is the tendency of a nucleophile to donate electrons. So tendency of nucleophile to donate electrons is called nucleophility. Okay, so with this we come to an end of this lecture. So we'll be meeting in the next lecture with some more interesting questions and with more interesting concepts. So till then, good luck and goodbye.